All right, so we are going to talk about what is called balance equations today. Okay, so I mean, the equations that you need to solve the unknown variables, which in this case is actually your deformation map. So, deformation map is the unknown. This is little f of big X is unknown. And so we have to find out equations which can be used to solve for this deformation map. And you see it has got three components, f1, f2, f3, denoting the three coordinates of the deformed coordinate. And what equations can we use is, for this we have to go to physics. For example, we know that for rigid body we can apply Newton's second law. So same thing can be applied even for deformable body. Okay, and even before applying Newton's second law, there is something called mass conservation or continuity. You must have heard about this when you took your undergraduate fluid mechanics course. You must have done this equation, continuity equation. Do you guys recall? Or mass conservation law?
Yes, sir.
Okay. So that was whatever you learned was, from the perspective of fluid mechanics. But now we will learn it in a more general way. And I think this will also be taught in continuum mechanics. So, and there are two ways to derive these equations. One is Lagrangian and then the Eulerian. And in continuum mechanics, both the ways are derived. But here we will restrict ourselves to Lagrangian. Okay? So let us think of mass conservation law, or what's called continuity equation. Okay, so think of your body in the reference state. That's the reference configuration. And this is the deformed configuration. And getting mapped through this deformation map. Now concentrate on some particular volume in the reference configuration. Okay. Suppose this volume is V naught. And after deformation, this volume may have become V. All right. So what do you think? What will mass conservation tell us? Just think of it from physics perspective. Can you say something? The volume V naught and V that you have here, they contain the same set of particles. You see, we are always tracking those particles. So neither particle is going out of this volume nor it is going inside the volume. You always have the same particles at every time because you are tracking the particles themselves, no? So there is no chance of particles being lost or new particle coming in. Okay, so we can write that V is the image of V naught under F. Okay, which also means that we are always looking at the same set of particles. All right. So, what do you think? What can we say? Can we say something from physics? Is something conserved here?
Sir, by same set of particle, do we mean like the number of particle will also be same?
Yes, of course.
So,
Because you see, as I'm telling you, you're tracking the particles. So if you
yes.
have five particles, it's the same particles which is there even after time t, because you are tracking the particles themselves. So there is no way for you to lose the particles, or there is no way to gain extra particles. So it is very important that you have the same set of particles.
It's a control volume, sir, or control space?
Well, it depends on what you have, what you call control volume. But this is more like, I would say, it's a control mass, because it's the same set of particles. Control volume in fluid mechanics, they say it's a control volume if your volume is fixed in space. It is not changing with time. You are looking at a same volume in the space, then we say it's a control volume. And if it's a control mass, then the volume of that mass changes with time. So you have two concepts: control mass and control volume. And what we are looking at, this is a control mass. Okay. All right. So what can you say? Is there something which is conserved for this control mass?
Mass will be conserved.
Mass is
Mass will be,
itself, sir. Mass is conserved.
that is true. So in physics, you can say that mass is conserved. Now let us see, can we use this to derive some equation? Okay. So what is the mass in the reference configuration, for example? So that is simply the integration over the volume V naught. And then you have to look at referential density, which we call by rho naught, okay, of big X. And then you have dV naught. So that's the mass in the reference configuration in the volume V naught. And physics tells us that this should be equal to the mass in the deformed state. But in the deformed state, your volume is V, and your density will be the current density. Right? The density can change now. So let's denote it by rho and also of little x comma t. Okay, can you see? This is Lagrangian, whereas this is Eulerian. This is called referential density, whereas this is called current density, and it is Eulerian. Okay. All right. Now, can I change the right hand side into undeformed volume, into an integration over the undeformed volume? You see, the right hand side, this is deformed volume. Can I change the domain of integration to undeformed volume? So you already know the way volume transforms, isn't it? So this, can we say that this is same as V naught rho of F of capital X comma T comma T into J into dV naught. Can we say this?
Yes, sir.
Right, so I have simply changed the domain from V to V naught. And this J here, that's the determinant of F, the deformation gradient tensor. And J is going to be a function of X, big X, as well as time T. Okay. Now let us bring the right hand side to the left hand side. And so we can say this is same as integration over V naught of rho naught of capital X minus rho F of capital X comma T into J of capital X comma T, and let's make the outer bracket with different color, into dV naught. Okay, so that's the equation. Well, this is the integral form, but now you see this volume V naught could be arbitrary. You could take any volume V naught and still come up with the equation that you just derived. So this is independent of V naught. Whatever V naught you take, you're always going to land up here. So take a very tiny volume, still this is going to hold. So, there is a theorem, what is called theorem of localization theorem. It's not a very big theorem. It simply says that the argument is 0. If the integration vanishes irrespective of what domain it is being integrated upon, then the argument must be identically 0. That's the theorem. Okay, so what this says is then that rho naught of capital X is equal to rho of F of capital X comma T into J of capital X comma T. Okay, so we can put it in a box. So this is called mass conservation or continuity. Mass conservation law / continuity equation. And this is Lagrangian form. I hope this is okay to all of you. Do you have any problem understanding this?
No, sir, this is okay.
Is the localization argument okay with all of you?
Hello.
Yes.
Sir, density is a scalar function.
Correct.
Okay.
Obviously, right? Density is scalar, right? It's mass per unit volume. Mass is scalar, volume is scalar. So density is also scalar. So here we have a function where output is a scalar, but the argument is a vector is a vector. See the f or big X or little x, they are vectors. So it's a scalar function of multiple variables. Okay. People get confused with this localization argument and they just think, how is this happening? So if you are also confused, then I can, give some explanation. What about Pulkit, is it okay with you?
Yes, sir. I think uh, because it is
Why?
integration over any domain.
Yes. So why should it vanish?
So this integration will always give us an answer 0 since these two are equal.
Correct.
Okay, sir.
Because you see, what you did is left hand side was equal to right hand side. You brought the right hand side to the left hand side. So this is then equal to 0, right? But how did we say that the integrand is 0? Because isn't it possible that in some domain it is plus, in some domain it is minus, so that when you integrate, it vanishes?
So, but it should be true for all the domains.
That's true, because it has to be true for all the domains. Therefore, it becomes identically 0 everywhere.
Yes, sir.
So isn't it like integral f of x minus g of x dx is equal to 0? The only possibility for the integral is when f of x is equal to g of x.
Yeah, I mean, if that holds for all domain,
All the
then
points in the domain of x. Yes.
yes, yeah, it is equivalent to that. But that also how you prove it. I can give you a very simple explanation through one-dimensional integration. Think of integration f of x dx from x1 to x2 and say that this is equal to 0 for all x1 and x2. So basically, if you plot, let us say this is f of x, this is f of x, and this is versus x, and you choose some x1 here, let us say x1, and another one, let's say here x2, well, maybe here x2. So in this domain, when you integrate, it's simply the area under the curve, right? The integration is the area under the curve. So here you can see that you have positive area as well as negative area, so the integral is vanishing. But this has to hold for all x1 and x2. Why don't you choose your x2 to be here? If you do that, then you can see this integration is now positive, right? So leads to a contradiction. Furthermore, just suppose that you can also prove it through, directly starting from contradiction. Suppose what you have to prove is that it is 0, right? So contradict the result and say that, let us say it is positive somewhere. So suppose that it is positive somewhere. Let us say it is like this. Then why don't you choose that itself to be the domain? Wherever it is positive, choose that to be the domain itself. And then in that domain, when you integrate, it becomes 0. No, it does not become 0, right? Because it is positive everywhere. Okay, so this leads to contradiction. So therefore, whatever you assume initially just cannot hold. So only way for it to hold is that it must vanish everywhere. Okay, so this is also called theorem of localization, and we are going to use it several times. And you see, this is the Lagrangian form of continuity equation. It is very simple. The Eulerian form of continuity equation, on the other hand, is not so simple. Can you guys recall the Eulerian form? Anyone can recall the Eulerian form of continuity equation?
Divergence of rho u is equal to 0.
Well, not really.
Don't remember.
You are missing a term. So it
Del
is,
rho by del t.
yes, del rho by del t
Yeah.
plus
Plus.
divergence of rho v, that's equal
Rho
to
v
0.
0.
And if the flow is steady, then del rho by del t becomes 0, and then you get what you just said. Okay? Now, can you derive this equation? What we did was the Lagrangian form of motion or Lagrangian form of equation that we derived, and this is the Eulerian form. How can we derive it? Any idea how can we derive it? Okay. Um,
So in undergrad, what we used to do was consider a infinitesimally small cubic element and then consider the flow of fluid in and out of that at x and x plus dx, and then we used to derive it like that.
yeah, that is true. But now you have to do it more rigorously. You have to take the domain to be arbitrary. The domain need not be cubic. And then you have to think, can we do it? Similarly, there is also what is called Reynolds transport theorem. Do you guys recall Reynolds transport theorem? This is an Eulerian form, by the way. It's always Eulerian. It says that suppose you have a quantity, let us say A, which could be scalar, vector, tensor, anything. A of little x comma t, or the vector A of little x comma t, or the tensor A of little x comma t. Okay, so the theorem says that integration of that quantity over the deformed volume. Okay, so this is the deformed volume which is changing with time, isn't it? And let's get the d by dt of this total derivative, d by dt total derivative. So this is equal to integration over the volume t, the spatial derivative, sorry, the local derivative del rho by del t. So this is not rho, this is any quantity which could be scalar, vector, tensor into dv plus del v of t. So del v is the boundary, is the surface of that volume of the same quantity, and then you have v dot n, and this is dA. Okay, so the first term is called local change, and the second term is called the flux. So second term is change due to flow of the particle from the volume, whereas the first term is due to change within the volume itself. Okay, this is flux due to flow. So this is also something you can derive. I can derive this for you guys. If you maybe let me derive this Reynolds transport theorem. Okay, so see, doing this is quite tricky. It's not so easy. And I recall when I did my undergraduate class, I always used to remember, okay, some step, but you don't really have to remember, just do it logically. So, okay, maybe I'll prove it for, let us say, a vector A, and then you can think of generalizing it to any quantity, which could be second order, third order, or fourth order also. So what we want to do is we have d dt of vt, and let us say I have the vector A dv, and A is in Eulerian form. Okay,
So do we also use this in solid, the Reynolds transport theorem?
well, if you have perfectly elastic body, then no, but if you have
Your voice is
viscoelastic,
breaking up.
if it's a perfectly elastic body, then we don't use it, but if it is viscoelastic, then we may have to use.
Okay, sir.
Yes. Okay, so now you see this d by dt is outside the domain of integration. You can't just bring it inside because the domain itself is changing with time. So you can't say that this is equal to integration over the volume T of d by dt of A. So this is not correct. Okay? So our first step should be to transform this integral into Lagrangian form. Okay, so let us do this first. So d by dt is still outside. I haven't taken it inside. But let's make it v naught into A of little f of big X comma t into j of big X t into dv naught. Okay, so this is just transforming it to Lagrangian form. But now the nice thing is you can bring this inside easily because v naught is not changing with time. That's the beauty of Lagrangian integration. You can bring the time derivative inside easily. So this becomes integration over V naught of d by dt of A into J dV naught. Okay, is that okay with all of you? And this then becomes, you have to use product rule now, right? So this is dA by dt. So remember that it is total derivative all along into J plus A times dJ by dt. Okay. All right. What more can we say? So you see, you have got dJ by dt to evaluate first of all. What is dJ by dt? So this is tricky. So I have to get d, and j is determinant of f. D by dt of determinant of f, total derivative. So I will, give this to you as an exercise. This is problem 3 of assignment 2. That this is equal to j times gradient dot v, and this is Eulerian. Eulerian divergence basically. Okay, so this is something you have to prove as part of your assignment. So I'm going to use this. So this becomes integration over v naught, and then you have dA by dt. Okay, so dA by dt plus A into J into divergence of velocity. Well, and you can take the J also outside, right? Into J into dV naught. And now you see this finally also becomes, you can convert it back to Eulerian domain. Isn't it? Okay. So now what can we do? You see, the first term is the total derivative, and A is an Eulerian quantity, which is a function of little x and time t. So you can recall, you can write it into two parts, isn't it? It's an integration over the volume V. You have del A over del t. Okay, that's a local acceleration. Sorry, local rate of change plus gradient of A multiplied with the velocity v, isn't it? And then you have plus A grad dot v. Okay, is that okay with all of you? See, I'm just going quite slowly here. And I can just pause here for maybe few minutes And just think what happens if your A is density. Although I chose A to be a vector, but as I told you, this A could be anything, isn't it? This A could be anything. So suppose A is a scalar quantity and it is density. So what is this left hand side going to give you? What is this equal to?
Derivative of mass,
And what should that be?
0.
That should be 0, right? And so all along it should be evaluated to 0 if A is density, right? So I'll just say a special case. So I haven't yet finished the Reynolds transport theorem, by the way. So special case, if A is taken to be rho. See, although I have written A as a vector, but as I told you, the derivation till now can be extended even if A is scalar, vector, tensor, anything. So if A is taken to be rho scalar, then to begin with that quantity is 0, and finally also this quantity should be 0, right? Del rho by del t plus gradient of rho, okay? And then here it will be dot v plus rho divergence of v dv, and this is equal to 0, right? To begin with it was 0, so this will also be 0. So, and you can do some more trick here. You can write it as del rho over del t plus, if you write it as divergence of rho v, just write it like this. And you can see that this will give you two terms. When you expand it, you will see that you get two terms. And now because this holds for arbitrary Vt, you can use localization. Because this holds for arbitrary Vt. See, Vt is Eulerian volume here, but this holds for arbitrary Eulerian volume also. So you can use localization to derive the differential equation of continuity. Okay. So just the byproduct of our derivation of Reynolds transport theorem. And this is the Eulerian. Anyway, so let me continue with the Reynolds transport theorem now. So I'm going to continue. Okay, so we have this quantity here. What can we write this as? If you, I'm just going to state that this can be written as divergence of A tensor product V. I'm very sorry, I'm not working it out, but you can write this. And how can you prove it? Just use indicial notation, and then you can prove what you have there. Okay, so I'll just write here. You can prove using index notation. So finally you have integration over Vt del of A del A by del T plus divergence of A tensor product V dV. Okay, and now you have to use Gauss divergence theorem. So the first term will be as it is over Vt dV, but for the second term you use Gauss divergence theorem when the quantity is a second order tensor. And I think we have worked it out, and it came out to be integration over the surface del Vt A tensor product V multiplied with the normal, outward normal dA, and which is finally integration over Vt del A by del T dV plus del V of T A into V dot N dA. Okay, so what we have proved is that the left hand side, you can recall, it was d dt of Vt of A dV. Okay, and I can box it now. So that's your Reynolds transport theorem, where A can be any quantity. We have proved it for vectors, but you could see in the entire derivation, you could have easily replaced A with scalar, vector, tensor, anything. Okay, and you see it's a general theorem, general proof. The domain could be arbitrary, need not be cubic. All right. Anyway, so this was digression. We just want to focus on Lagrangian form of balance equation. And the first one that we got is the mass continuity, which simply says rho naught of big X is equal to rho of F into J. Okay, this is the first equation which allows you to obtain the current density. If you know, see, this referential density will be known, and this is unknown. So this equation allows you to obtain the current density in terms of the referential density. But you see, this is not an independent equation because this J here is also an unknown. J is the determinant of deformation gradient, and deformation gradient is the gradient of deformation map, which is also an unknown. So this is not an independent equation that you can solve for rho. So you have to get more equations now. See, to begin with, you thought that your F, the deformation map, is the only unknown. But when you applied mass conservation, you see that rho is also an unknown. Okay, so now we have rho and also the deformation map as unknowns, and you have already gotten one equation. So the next thing that we can use is Newton's second law. Okay, so let's apply Newton's second law. See, till now we have applied Newton's second law to rigid bodies, but now we are going to apply it to deformable bodies. Okay, and we in undergraduate solid mechanics, you may have also done it, but you took cuboid element and derived the balance equations. Do you guys remember that undergraduate solid mechanics, you must have taken a cuboid element, written down the stress components, then sum the forces in the x direction to obtain a derivative, to obtain a differential equation in stress. Can you recall? Anyway, if you don't recall, then you just have to go back and see. But now we are going to derive the Lagrangian form of balance equation, and assuming the volume to be of arbitrary shape. There is no need for us to take that volume to be cuboid. Okay. So again we have, so I'm just going to write here, we have to now use Newton's second law. Now at several places they also call it linear momentum balance. Okay, so you have now the reference configuration and the deformed configuration. All right, so now the thing is, this Newton's second law you can apply not just to the entire body but also to a arbitrary small part of the body. See, if you think of it from particle perspective, every particle has to follow Newton's second law. Likewise, a set of particles also has to follow Newton's second law. Okay, so you can think of a volume in the reference configuration and start tracking the particles here. So these set of particles, if you apply Newton's second law to it, it's going to follow. And remember, we always apply balance equation. We always apply Newton's second law to identifiable set of particles. What does this mean again? Is that you must focus on same set of particles all the time, and you have to see what is the rate of change of linear momentum of those set of particles. So your particles must not change. The particles should not come out or a new particle should not get in. If that happens, then you can't apply Newton's second law in the original form. Okay. So what does Newton's second law tell us? It's very simple, that rate of change of linear momentum, if we denote linear momentum by P, then rate of change of linear momentum of the system is equal to net external force acting on that system. Okay, this is the Newton's second law. So you have to always identify the system, and you can't change the system when you are taking the rate of change, or when you're taking the derivative. You cannot change the system. It's not like you can also interchange the particle. You are not allowed to even interchange the particle. It must be the same set of particles, and then only you can apply the Newton's second law. Okay, so this means that we have to again think of particles comprised in this volume V0 and see how that is evolving in time, how the momentum of that volume is evolving in time. Okay. So in the current configuration, we have that volume V here. So let us take that outside. When you take it outside the body, that's your V, and it's a function of time. So what are all the external loads that is acting on this body? So you will have traction acting on this body from the remaining part of the body, isn't it? So those are these tractions. From the remaining part of the body. And you know that the traction T is equal to sigma into N, where N is the outward normal. Okay, so this is the contact force on this small volume V acting from the other part of the body. What are the other things? You can also have body force, for example, the gravitational force, isn't it? So let me draw that picture here again. So this is V of T, and you have the traction, and traction only acts on the surface. So this is also surface force or contact force. But apart from this, you can also have what is called body force, which acts throughout the volume of the body. For example, gravitational force. So gravitational body force, so it is force per unit volume. Okay. So you could write it as rho into G. In case it is gravitational. Otherwise, you simply write it as, let us say, rho into B, where rho is the current density and B is the force per unit mass. Okay. So the Newton's second law, when we apply, you see it has got two terms, left hand side and right hand side. So let us write down both the terms here. So the left hand side is d by dt of the linear momentum of this system. And what will be the linear momentum? So can you recall what is linear momentum for a particle? Anybody? Vinayak?
To its velocity.
Mass
Mass into velocity, right? But
Yes, sir.
here you see this body has got several particles. So you have to sum over all the particles, mass times velocity. And in fact, because we have infinite particles here, that summation becomes an integration, triple integration. And any particle will have mass, current density rho into dv. That's a small mass, and you have to multiply with the velocity v, isn't it? So this is the mass dm. So that's the left hand side of Newton's second law. On the right hand side, I have to write down the total external force, which in this case you have the traction force and the body force. So the traction force is then the integration over the volume, over the surface. That's del Vt of sigma into n into dA, isn't it? And then you have body force rho into B into dV. Okay, so you see this we wrote down on a Eulerian volume, and we want to derive the Lagrangian form of linear momentum balance. So we simply have to convert all the domains here into Lagrangian domains. So that's the first step. Convert all the domains into Lagrangian domain. Okay, so the left hand side you have d dt, and then it becomes integral over v naught, and you have rho d. Okay, so dv becomes j into dv naught. Okay, and then you have velocity v, but I will now call it v with a hat, or maybe capital V. So capital V, it just means it's the Lagrangian velocity, capital V, which is a function of big X, comma t. So the relationship is small v of little x, comma t, or maybe I should say capital V of big X, comma t is equal to small v of f of x, comma t, comma t. Okay, so that's how you relate the Lagrangian and Eulerian velocities. So it's just a point which is changing, but the velocity itself is the same. And that's how you can write in Lagrangian and Eulerian forms. Okay, so I'll just say that this is Lagrangian velocity, whereas this is Eulerian velocity. Okay, and then you can come on the right hand side. Okay, here what you can do, can you recall now that we had converted from deformed surface to undeformed surface? So this becomes del V naught, and you see you have sigma n dA, which you can write as capital P into big N into D capital A, isn't it? Where big P is now the first Piola-Kirchhoff stress tensor. So this is by definition. I hope this is clear to everyone. Is it okay to everyone?
Yes, sir.
Okay. Then you have plus, again the integration over the undeformed volume, rho b j dv naught. Okay. Now you see you have to use the Lagrangian form of mass continuity. What does that tell? That rho into j is equal to rho naught. Can you see the Lagrangian form here? Rho into j is equal to rho naught, the referential density. So that simplifies. So here I am now using mass continuity. You have d by dt integral over v naught rho naught into big V, big X comma t dv naught, and that's equal to integral over del v naught big P big N d capital A plus, you see things are becoming so easy now, rho naught B dv naught. Okay, is that okay? Now what are the remaining, what is remaining? So you have to bring this dy dt inside and maybe convert this to volume integral. So convert to volume integral so that you have everything as a volume integral. So bring all of them on the left hand side and set it equal to 0, and then you say that because it holds for any volume, use localization then. Okay, so let us do that. So left hand side is now easy because you are integrating over the reference volume, which is not changing with time. So you can simply slide your dy dt inside, and also see that in the integrand you have rho naught into v, but rho naught is not a function of time. So all d by dt goes to big V. So you have rho naught into del v by del t. You see that d by dt has now become del v. It's just because you have v in the Lagrangian form written here. If you have any problem, please feel free to interrupt me. And what can you say about this surface to volume thing? So you have to obviously use Gauss divergence here. Use Gauss divergence theorem. Can you recall what will this be? Anybody? Devjit? Can you tell me from the Gauss divergence theorem that we have learned?
Yes, sir.
Yeah, tell me. So it's a second order tensor multiplied with the outward normal.
Then del dot p हो जाएगा simple divergence v.
Exactly, L dot P हो जाएगा. So it becomes volume integral divergence dot P, and this divergence is the Lagrangian divergence, remember, plus V naught rho naught into B dV naught. So everything you see now is an integral over the undeformed volume. So you can bring them all under the same integral, and you have V naught divergence dot P plus rho naught B minus rho naught, and you see what is this thing here, del V del T.
Acceleration.
Exactly, so this is del V del T at fixed capital X. So when you fix your capital X, then you are looking at acceleration then, and this is what also it is originally. See, you have to do dy dt of this velocity here. So what you get is acceleration, and I'll just, because it is Lagrangian, so I'll use capital A. dv naught. Okay, so now use like very simple localization argument because this holds for any volume. And so what you get is divergence dot p plus rho naught b is equal to rho naught a, which you could also write it as rho naught del 2f by del t2. Okay, so I can now box it. So this is called linear momentum balance equation. In short, you have LMB. Okay, linear momentum balance. Any query? And its Eulerian form is also similar, and it turns out to be divergence of sigma plus rho b is equal to rho times acceleration. This is Eulerian, and you have to remember that this is Eulerian divergence. So you can see this form is similar. Unlike the mass continuity, here the form is similar. It's just that in Lagrangian you have first Piola-Kirchhoff, and in Eulerian you have Cauchy stress tensor. Okay, you see so neatly the Lagrangian form has got rho naught.
In Eulerian forms are that rho will be the function of time also.
Yes, of course. So here this rho, as you see, it is without naught. So it is the Eulerian density, which is also changing with time. Okay.
Sir, you said it's Eulerian divergence. I didn't understand Eulerian divergence.
Okay, so see, it just when you do divergence, what is the formula? It is del by del. I mean, derivative with respect to three coordinates, right?
Yes, sir.
So now those coordinates, are they the Eulerian coordinates or the Lagrangian coordinates? Are they spatial coordinates or the referential coordinates? If they are referential coordinates, then you say it is Lagrangian divergence. If they are with respect to spatial coordinate, then we say it is Eulerian divergence.
Okay, sir. Got
Yeah,
it.
and they are both different.
Sir, so
Okay.
Eulerian function is basically for
Yes.
solving problems related to fluids, and here, like these two equations are also for fluids and solids.
Right. I mean, both can be applied to fluids as well as solids. It's just that one of them turns out to be convenient. For solid bodies, usually Lagrangian form is convenient, which we'll learn later on why it is so.
Okay, sir.
Okay, it is mainly because of the constitutive equation. But let us postpone it to later discussion. All right. But you can use both Eulerian and Lagrangian for any body, whether it is solid or fluid. In fact, these days people talk about Lagrangian tracking of particles in fluid mechanics. So basically, they want to track the particles themselves. I mean, they say that there is some advantage of using the Lagrangian form of equation in fluid mechanics. So that is quite non-conventional, but there is some advantage.
Sir, we have been told in our UG that in Lagrangian approach, since we track each and every particle, although it's like the calculations will be very huge, but the analysis will be quite exact. Like that, we have been taught.
Well, both are exact, whether it is Eulerian or Lagrangian. You see, both are correct equation, right? They are exact equations.
Yes, sir.
So, I mean, both are correct formulation. It's just that solving one of the formulations is easier for somebody. For example, for fluid mechanics, it's usually the Eulerian form which is easier, and for solid mechanics, it is usually the Lagrangian form which is easier. But both are exact equations.
Okay, sir.
Yeah,
So it's just a matter of our convenience, like which to choose. Both will give exact result. We can choose any,
correct.
but based upon our convenience, we have to select one.
I mean, you should not say based on our convenience, it is based on the system that we are
Yeah, yeah,
looking at.
yes, sir.
Right. Okay, so now what is the status right now? Let us have a look at all the equations that we have derived. So one was rho naught is equal to rho into J, and then we have divergence dot P plus rho naught B is equal to rho naught del 2 F by del T2. So how many unknowns are present here? So you see this rho is an unknown, this F is an unknown, J is also an unknown, but this can be obtained through F, right? Once you know F, take its gradient, you get, and then the determinant, you get J. P is also an unknown. So how many unknowns are present here? J has got 1, sorry, J is obtained through F, no? So F has got 3 and P has got 9. So total 12 unknowns. But how many equations? 4 equations only till now. So obviously we can't stop here. We have to derive more equations. So you have to think from physics what other equation can be used. So we have done mass continuity, we have done Newton's second law, there is linear momentum balance. Is there something else that we can use?
Sir, angular momentum balance.
Exactly. So you can also use angular momentum balance. So let us try to do that now. Okay. But I'm not going to derive it. I'll give it to you as an assignment. But you will see that it is only little bit more difficult, not so much. So angular momentum balance is also there. So just like linear momentum balance, this is going to also hold for any volume of the body. So we'll call it as AMB in short form. Okay. So again, you have that volume V of T, and you have those forces acting, right? That is traction T is equal to sigma times N, and then you have body force, which is rho B. And let us think of doing the moment balance about a point O. Okay, that's the origin of the coordinate system. So what does the angular momentum balance equation tell us? It is very simple that d by dt, rate of change of angular momentum, we denote by h, of the system about the point O. Okay, this is equal to net external moment about the point O. All right. So this is a simple form where O, there are many different forms of angular momentum. It is not so easy. If you have done your engineering mechanics course in UG first year, you would have noticed that this is really a difficult form. Depending on whether O is moving or O is stationary, you can get extra terms here. But here we will say that O is stationary, so we have the most simpler form, the simplest form of angular momentum balance equation to work with.
Moment of inertia will come into the picture.
Yeah,
This
that's also going to come into picture, obviously.
real.
Okay, so now, yeah, this is really difficult, I have to tell you. So let us work out the left hand side and right hand side. So again, it has got several particles, infinite particles, so obviously it becomes an integration. So you have d by dt, three-dimensional integration, and then the angular momentum of a particle, which will be position vector of the particle. Think of a particle P here, of the particle with respect to O, cross product mass times velocity of the particle, isn't it? That's the angular momentum. And mass, we have learned it is dm into v, and dm is nothing but rho into dv, okay, and into the velocity. Is anyone have any query? Anybody having query? So that's the left hand side. Now come back to right hand side, and this becomes the moment due to traction. So that's obviously over the surface, and you have position vector r with respect to, and let us say you are looking at a point x on the surface, small x. Likewise, this p also could be small x itself. I don't have to use p here. It's a small x. So you have, so r of a small x with respect to O, which is simply x itself, isn't it? You can recall that x is the position vector from O. So, and then here you'll have x cross product the force of traction, which is sigma n dA. All right, and then you have the moment due to the body force, and that's again x cross product rho b dv. All right, so this is the net balance. Anybody having problem?
Yeah, excuse me, sir.
Yes.
Sir, in the current configuration, we are taking body force as a rho b.
Yes.
But it should be same to the reference configuration as the mass is constant, means mass is conserved. So, if you
Yes,
take
but
mg,
yeah, I understand what you're saying. See, we are defining body force as force per unit volume, and in the current configuration it is force per unit deformed volume, whereas in the reference configuration it is force per unit undeformed volume. Therefore, in the deformed you have rho b, and in the undeformed you get rho naught into B.
Then, sir, it mean that the body forces are different in the current and the.
No, 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 it's the same body force. It's just that you are expressing them in Lagrangian and Eulerian forms. So the
Okay.
Lagrangian and Eulerian forms are different, but it's the same body force.
So body force magnitude are same.
I mean, physically it's the same body force, but in Eulerian we say body force as force per unit deformed volume. And Lagrangian
Okay.
it is force per unit undefined volume. So now these two are different. Force per unit undefined volume is not equal to force per unit defined volume, right?
Okay.
So isn't body force force per unit mass?
Well, it depends on how you're defining. Maybe you may have heard it somewhere, it is force per unit mass. But here we are interested in force per unit volume because you see we are doing an integration over the volume, right? So therefore
Yes.
we want something like force per unit volume which you integrate over the volume to get the total force.
In linear momentum balance, did we define it as force per unit mass?
No, no, no. It's B which is force per unit mass,
Yes, yes, yes,
but not rho times B is then force per unit volume.
yes. Okay, sir.
Yeah. Okay. So the first thing, of course, is to convert them into Lagrangian form. So it is dy dt integral over V naught, and then you get x. See, small x, you can't change small x to capital X. You should be careful. I mean, obviously, you can say small x to be little f, so that it is coming from capital X. So little f cross product, and then you have rho naught big V dv naught, okay, and this is equal to del V naught of little f cross product, and you see sigma and dA, again you use the equivalence and you write it as P capital N D capital A. That's from the definition of first Euler Kirchhoff. And then the last term, it is plus big V naught little f cross product rho naught B dV naught. Okay, I hope this is clear to everyone. All right. And then I can slide this thing inside the integral, isn't it? So you have integral of V naught, and you see it becomes del f by del t cross product rho naught capital V plus f cross product rho naught del V by del t, product rule. But it's becoming partial now because it's Lagrangian. And the right hand side is the same as it was earlier. Okay, so then you have to see, look at this first term here. Del f by del t is nothing but V itself, and you're crossing with rho naught v. Isn't it 0? Right? So this vanishes. Roshan, are you following? Roshan? Are you there, Roshan?
Yes, sir. I am follow, sir.
Okay, very good. So F cross rho naught, and you see what is del V by del T? That's simply acceleration, big A, dV naught, and that's equal to integral over del V naught F cross Pn dA plus integral over V naught of F cross rho naught into B into dV naught. Okay, so now the trick is now to convert this thing into volume integral, isn't it? So you have to use some kind of Gauss divergence theorem. Do you know what is this going to become? We haven't seen this thing in our, I don't think we saw this, how to apply Gauss divergence, but we have to use some kind of Gauss divergence theorem. Can you use it? Do you think you would be able to do it? Well, so I'm going to give this to you as a fourth assignment. So this is problem 5. I won't give you more. Okay? So think of what does this become in tensor form. And final result, I'm going to write the final result convert this into the volume integral, and then you have to use localization. Okay, so finally what you get is that PF transpose, the transpose of this is same as PF transpose. So that's the A and B, the Lagrangian form of A and B. Do you know what is PF transpose? Can you recall the relationship between P and sigma? So sigma, I guess, is 1 by det F into PF transpose, isn't it?
Yes, sir.
So this simply is telling us that sigma transpose is equal to sigma, the A and B, the Lagrangian form. This is the, sorry, Eulerian form. Okay, so I'm going to stop here.
Sir, like in Eulerian form, we have Cauchy state of stress and then corresponding Lagrangian form is pk stress. So, do we have any such concept for representing strain also?
Yes, yes, of course. We have the strain that we learned is called the
Cauchy.
Lagrangian strain tensor, half of C minus I, right? So C is the right Cauchy Green tensor, and half of C minus I, which we wrote as epsilon, is the Lagrangian strain tensor. And
Sir, this
likewise, yes, please go
sir
ahead.
half gradient of U plus gradient of U transpose, that is also strain only, no?
No, but that's the linear
Like,
elasticity strain.
okay, sir.
That's the strain of linear elasticity. See, the strain that we have here is epsilon is equal to half of C minus I, which is half of F transpose F minus I. And when you put F as I plus grad U transpose into I plus grad U, I think I did it perhaps, minus I,
Yes, sir. You
then this
did.
becomes half of grad U plus grad U transpose plus grad U transpose into grad U. So this is the Lagrangian strain tensor, finite strain tensor. And when you linearize this in U, because in linear elasticity we only want the linearized part. So after linearization, you get half of grad U plus grad U transpose, which is also called the linear elasticity strain tensor or infinitesimal strain tensor. Okay, but for finite elasticity, that's the Lagrangian strain tensor, or maybe say here. And there is a counterpart, Eulerian strain tensor is also there, which is defined as half of I minus what is called B inverse, where B is FF transpose. Instead of F transpose F, it is FF transpose. Okay, and this is called Eulerian strain tensor. And when you linearize, you get back the same thing. So for finite elasticity, the Lagrangian strain tensor and Eulerian strain tensor, they are different, but after linearization, both give you the same formula. Okay.
So which is why the expression for shear in solids and then also in fluid that we get is same. Deformation of F deformation expression in fluids, that half del U by del U, U1 by del X2 plus del U2 by del X1.
Yeah, I mean for linear elasticity, it's the same. In fluid mechanics, we only talk of shear strain rate.
Sir, in fluid for shear, viscosity plays a major role, right? So,
Yeah. So what do you mean?
sir, like I was thinking maybe that's the reason why we never talk about we in solids shear strain. Instead of that, they go for shear strain rate or something because
You see, all that you are talking right now is it comes under the domain of constitutive relationship between stress and kinematics. So we will touch that later on. Okay, and if you don't see that in continuum mechanics, then I will certainly try to do it here. Okay, but for now, let us just concentrate on what we learned today. Any query based on it?
सर
हाँ.
सर हमारे पास जब हमने स्टार्ट किया था तो कंटिन्यूटी इक्वेशन तो हमारे पास दो अननोन्स थे, बट धीरे धीरे करके वो भी बढ़ के आया, 12 पे आ गया है.
राइट राइट.
सो हम लोग
करेंगे उसके बारे में. ये फाइनली तो हमारे पास जितने अननोन से उतना इक्वेशंस होना चाहिए. सो दैट्स अ वेरी गुड ऑब्जर्वेशन ऑफ योर्स कि अननोन्स तो बढ़ते जा रहा है, तो इक्वेशन कहाँ से
यस
आएगा. तो उस सब के बारे में बात करेंगे हम लोग नेक्स्ट क्लास में.
ओके.
यस.
okay, sir, thank you.
Okay, thank you very much.